Good evening. Welcome. Second semester AP Stats and your first set of online notes. Chapter 7 is about sampling distributions, and it's really, really important. These sampling distributions are what we base a lot of our inference procedures on. I feel like I say that a lot. I mean, it's based on probability models. It's also based on what we would expect to happen if the population had a particular measure. And then we'll eventually sort of flip that around and think about it in a different view. But a sampling distribution, and there's that word again, distribution, which is just a list of values that a variable can take and how often it will take it. Is a distribution that shows what would happen if we took many, many samples from a population. Because that's what we do, right? In stats, that's what we do. We take samples from a population and try to use the sample data to make conclusions about the population as a whole. And so it would be helpful to know that if a population had a particular measure, then what would all of those samples, if we took every possible sample, what would those samples look like? And we'll get into that a little bit more later. A couple of things real quick that we can get to tonight and then get it set up to do some things in class tomorrow is what is a parameter? And what is a statistic? And we've come across those words before, but I think a little bit prematurely. A parameter is any number, okay, and this is a parameter, any number that describes a characteristic on a population. A characteristic of a population, I suppose. So anyway, it's a measure on the population. That's what a parameter is. Parameter population, PP, right? Parameter is anything that we measure, any value that we get from a population. Now, the deal is, and I'm trying to keep these separated, but the deal is, usually these are unknown. Any measure on a population, well, the only way to know that for sure is to take a census, right? And a 100% accurate census to where we talk to or look at everything or everybody in the population. That's the only way we're really going to know the true value of any parameter. And we can't do that. We've talked about that before, and I think it makes enough sense to know that we really can't do that. So what we do is we take samples and we let samples tell us, as long as we do everything correctly. Now that's where a statistic comes in. A statistic is any number that describes a characteristic of a sample. Right? And so hopefully taking a sample and calculating the mean of that sample gives us some insight to the mean of that same measure on a population. And so these will match, right? Now the notation's a little bit different, but these will match. And so again, the idea is ideally we can use a statistic to estimate a parameter. Sometimes we can, sometimes we can't. Now the good news is very often we know going in if a measure on a sample is going to give us any indication about the same measure on the population. And we'll talk about that a little bit more a little bit later. So some notation. So we have some different notation. Parameters and statistics are different. Even though it might be the same measure that we're talking about between a population and a sample, they are different. do something called sampling variability that we'll get to in just a second. But so here we go. Mu, sigma, and p are all parameters. Mu is the mean of a population. Okay, these are all parameters. PP, population. Sigma is the standard deviation. We've seen these before. And P, lowercase, this is supposed to be a lowercase p, is going to be a proportion, any proportion of a population. Okay? Our statistics sample statistics, SS, are, again, the same measures that we might take on a population, but we got to have different notation because they're not always the same. Numerically speaking, they're not always the same. So X bar is going to be the mean of a sample. Little s, or sometimes S sub x, is the standard deviation of a sample. And then p hat, and we've seen hats before in terms of regression and trying to make predictions. And that's kind of what we're doing with samples, trying to make predictions on the population. But p hat is any proportion that we might measure for that sample. So it's a proportion of a sample. So they do match up. Sometimes they're not the same. X bar and mu may not have the same value. As a matter of fact, S sub x and sigma are even calculated differently in terms of the formula. S sub x is divided by the n minus 1. Sigma is divided by n. It's a truer average. Okay? I don't want to get into that too much. It's kind of outside of our scope, but just understand that it's important to understand the difference between these notations and what they stand for. Okay? And so we got to be able to pick that out. A couple of examples here. Identify the population, the parameter, the statistic, and the sample for these examples. Okay? All right, so a pediatrician wants to know the average height of 10-year-old boys. So she takes a sample of 50 patients and calculates the average height to be 48 inches. So let's go through this guy real quick. What's the population? And again, our scope of inference, we talked about that back in chapter 4. We've got to be kind of specific. So our population is going to be all 10-year-old boys. That's not supposed to be a B. 10-year-old boys. The parameter right is going to be mu, which is the mean height of 10-year-old boys. Okay, our sample, right, is just the 50 patients. That she takes a look at. And then the statistic is X bar, which is 48 inches, right? It's just the mean of that sample, okay? Try B real quick. Write that out. I'll stop the video, or you can stop the video, and give it a shot, and then I'll come back and show you what I come up with. Okay, so what you come up with? A Pew Research Center poll asked 1,102 12 to 17-year-olds in the U.S. if they have a cell phone. Of the respondents, 71% said yes. Okay, did you get this? The population are all 12 to 17-year-olds in the U.S. And did you include in the U.S.? You have to, right? Again, it's our scope of inference. We can't include, obviously there are other 12 to 17-year-olds out in the world, and the proportion of those 12 to 17-year-olds who own a cell phone might be very different. Might be very different in China as opposed to Germany, as opposed to Somalia, right? And so we've got to make sure that we're very specific about our population. The parameter is P, let that be P. That's the proportion of the 12 to 17-year-olds in the U.S. that have a cell phone. Our sample is 1,102, the 1,102, 12 to 17-year-olds in the U.S. that were sampled, that were talked to. And the statistic is P hat, which is 0.71 or 71% that said yes. Okay? Again, I think hopefully it's pretty straightforward. Just make sure that you're as specific as you can when you're identifying the population in the sample. Again, communication being a big factor here. Make sure that you can communicate exactly what the population in the sample is for anybody that might be looking at your work. Okay? So there you go. Hopefully that was pretty easy enough. Now, I'll ask you this, and I'll probably ask you again in class at some point, but I'll ask you, let's say that 71% of 12 to 17-year-olds in the U.S. have a cell phone. Let's say that 71% is the population measure, right? If I take a sample, 1,102, of 1,102 of those 12 to 17-year-olds, is that sample going to give me 71% of them saying yes, they have a cell phone? Automatically, because the population is 71% owning a cell phone or having a cell phone, does that guarantee that my sample will give me the same measure? Hopefully you're shaking your head no, right? I might take, as a matter of fact, in this particular sample here, if I took a different sample of 1,102 12 to 17-year-olds, would the 71% here still, would I get the same? Would I get 71% having a cell phone? And hopefully you're thinking to yourself, no, not necessarily. It might be any number, 69%, 52%, 93%, whatever. That is your sampling variability. Okay, that's what we mean by sampling variability. And so what is sampling variability? It's really the basic sense that the value of a statistic, I don't know, let's word this correctly, the idea that the value of a statistic, statistic, been a long break. The value of a statistic will vary from sample to sample. Okay, so that idea is, all right, so the first sample up here said that 71% of 12 to 17-year-olds in the U.S. have a cell phone. And like I said, if we take a different sample of 1,102 12 to 17-year-olds in the U.S., there'll be different 12 to 17-year-olds probably, and so therefore result in a different percentage of those that have a cell phone, might be 68%. So which sample gives us a better idea of how many 12 to 17-year-olds in the U.S. that have a cell phone? In other words, the 71% and the 68%, which one gives us a better idea about the whole entire population? Right? To figure that out, what we do is we don't just take one. We'll take a large sample, a large number of samples, right? So to make sense of our sampling here, to make sense of sampling variability, right? We'll take a large number of samples. Get that out of the way. Right? Obviously find the statistic, calculate the statistic that we want. Okay, graph those values. And then take a look at the distribution, right? Examine the distribution. Take a look at it for shape, center, or spread. Outliers, that kind of thing, and try to determine if the samples give us an idea about the actual population. And so this last part, step 3, graph the values, that's what we call a sampling distribution, right? A sampling distribution is simply a graph, it's a distribution that shows all the values taken. So this is just a distribution that shows all possible that shows the values of a statistic in all possible samples and how often those values occur. Okay, that's still the idea of any distribution, right? It's the values of whatever statistic it is that you're measuring in all possible samples and how often those values will occur. So, you know, we ideally won't just take one sample. We'll produce a bunch of samples and then graph those samples and create the sampling distribution. Okay? What's the difference between the distribution of the population, the distribution of the sample, and the sampling distribution of a sample statistic? There's a huge difference, and this is something that I think we need to take a look at in class. Okay? So we'll stop here. We'll do a quick activity in class tomorrow that'll show the difference between the population distribution, the distribution of sample data, and then a sampling distribution. And this is going to be a tough sort of concept to grasp, so we've got to make sure we understand the sampling distribution really well going forward. So look forward to that. We'll stop the notes here and get into our activity to describe these 3 things and then get you into some homework as well. Okay, I will go ahead and put the homework in with the text for the notes. Guys, have a good night. We'll see you tomorrow.